All right, let's take a look at one final example with linear kinematics. So here we have a car that's traveling along a highway at a speed of 33 meters per second. When the driver sees an obstruction 145 meters straight ahead, it takes the driver 1.75 seconds to react and begin braking. So that is our question, and after reading the question, what I want the first thing for us to do, I want to visualize what's happening, and a good way to do that with these problems is, even though it's not asking for it in the question, is to sketch out kind of a rough velocity time graph. So I'm going to draw a little velocity time graph here. Now it doesn't have to be too accurate or too fancy, but we put time on the x-axis and we put velocity in meters per second on the y-axis. Okay, so let's take a look at the information we're given. So the car is traveling 33 meters per second. So let's draw a line. This will be our 33 meters per second here, all right? 33. And then when the driver sees an obstruction 145 meters straight ahead, then takes the driver 1.75 seconds to react and begin braking. So what we're going to see is at this point here, this will be our 1.75. This is 1.75. We are going to see our velocity come down. This is when the brakes are applied. So here, brakes applied. So even if you're not quite able to put together a sketch of what's happening, it's always a good idea to do your best to at least get a visual idea of what the question's asking, so we know some kind of visual picture of what's happening. So now that we've got this established, let's start with part A. So what distance does the car travel before it begins to slow down? So this is asking for the time between the driver sees the obstruction and the time it takes to react. How much distance is traveled in that time? So what we're going to do here is we're going to start with step 1, and you will recognize these steps from our previous linear kinematics problems. Step number 1 is to organize our variables. Organize our variables. All right. Just going to do these in green. So in this question, the variables we're concerned about are how fast we're traveling. So when the driver sees this obstruction, he's traveling with a velocity. Here it says in the question 33 meters per second. So we have a velocity of 33 meters per second. And what distance does the car travel before it begins to slow down? We need a time. So we're traveling at a certain speed, but for how long? Well, the reaction time of the driver is 1.75 seconds. So the time is 1.75 seconds. And what variable are we looking to find? Well, we are looking for distance. So our unknown here is going to be delta D. That is our unknown. And you'll see in the question we're given this other piece of information, that how far the obstruction is away from the driver. This piece of information we're not concerned about for part A, because we're not concerned about how far away the obstruction is. We just want to know the distance the car travels before the brakes are applied. So we've got our variables. This is all we're going to need. This brings us to step 2, which is to choose an equation. Step 2, choose an equation. And to do this, we look at the variables we're given. So we're given velocity, time, change in distance, displacement. And that tells us which equation we're going to use. So let's go over to our chart, and you'll see a lot of times with previous questions, we've got 4 variables, and we'd be looking at one of these equations. This one's going to be a little bit different. If you look at this equation down here, I've called it the bonus equation. That's because it's not one of our typical 5 linear kinematics equations. This one is more of a, it's a simpler one with only 3 variables, and this is used when you have a displacement, velocity, and a time. So in this case, this is actually the equation that we want to use. So the equation that we're going to use is that the distance traveled is equal to the velocity multiplied by time. That brings us to step 3. Step number 3, and that is to plug in our variables. Plug in variables. So I'm going to start by rewriting this equation down here. I'm going to bring it up. So delta D is equal to velocity times time. Now let's plug in our variables. So we're going to come back to step 1. Look at, okay, so for delta D, we have an unknown value. So when I plug that in, I'm just going to keep it as delta D. Then for our velocity, we've got a value of 33 meters per second. 33 meters per second. And then for time, let's look at our given, 1.75 seconds. 1.75 seconds. All right, so we've got all our values plugged in. Let's simplify this equation a little bit. I'm going to just change the colors so it's clear to see what is our unknown. So our unknown here is just delta D. And now, with other questions, sometimes you'll have to rearrange the equation to isolate your unknown on one side of the equal sign. In this case, we got lucky, and delta D is already isolated by itself on one side of the equation. So all we have to do is type this into our calculator, and that will give us an answer for delta D. And I encourage you to follow along with me. Type this into your calculator. We got 57.75 meters. And before we give our final answer, we want to look at significant digits. So in the question, our values all have 3 significant digits. So in our answer here, it's going to be good to provide just 3 significant digits. This 7 will round up to an 8 because of the 5. And that will be our answer. And I'm going to write a little statement to go along with that. So what does this mean? Well, this means that from the time that the driver notices the obstruction to the time it takes him to begin braking, so his reaction time of 1.75 seconds, the car travels a distance of 57.8 meters. So the car travels 57.8 meters before it begins to slow down. and that is 57.8 meters after the driver first sees the obstruction. All right, so that is part A. Let's move on now to part B. It asks us, how long will it take the car to stop once the brakes are applied, assuming that the car stops just before the obstruction? Okay, so let's start off here with step 1 of organizing our variables. Step 1, organize variables. So what values do we know? Well, we're going to be going back to our original question here. We know that the initial velocity, 33 meters per second. So V1 is equal to 33 meters per second. And another piece of information that we know is we are looking to find how long it takes the car to stop. So when we stop measuring, our V2 is going to be 0 meters per second. We want to see when the car stops. So that's our V2. We also have a distance. So that is a distance here when the car is stopping just before the obstruction. So we're going to have to do a little bit of a trick here. We're going to see that initially the obstruction is 145 meters away. So let's write that for now, 145 meters. But, and I want to see if you guys are able to catch what I need to do here. This is not the value we're going to use for delta D. What I want you to notice is that once the brakes are applied, we've already traveled a certain amount of distance. So once the brakes are applied, the obstruction is no longer 145 meters away. It's going to be a little closer because some distance has been traveled. So what we have to do is we have to subtract this distance. And because we want our answer to be accurate, we're going to be using these extra decimal points and not this rounded answer. So we're going to be using the actual distance that the car traveled before the brakes are applied. So minus 57.75 meters. And when we type that into our calculator, get a distance of 87.25 meters. So that's after the driver's reaction time of 1.75 seconds, how much distance is left until the obstruction. And now it's actually 87.25 meters. And then our fourth variable, we are looking for a time. How long will it take? So that's time. How long? And that is our unknown. That brings us to step 2. To choose an equation. So let's choose an equation. Looking at the variables, we have a V1, we have V2, we got delta D, and we have time. So which equation are we going to use? Well, let's go back up to our chart. And let's see which equation uses all those variables. Let's look. V1, V2, delta D, and time. So it looks like we're going to be using equation 4. And again, your teacher or your textbook might have these equations labeled with different numbers. So it's important to actually look at this equation here and not just the number. So take a look at this equation. So we're going to take this equation because it uses all the variables that we need. So because we need these variables, we're going to be using equation 4. Right, step number 3 is to plug in our variables. And I hope this is starting to get repetitive now. Every question is going to be these same steps. So again, let's rewrite this equation. Delta D is equal to V1 plus V2 divided by 2 multiplied by time. Right, let's plug these in. So for our distance, remember we have 87.25 meters. 87.25 meters. That is equal to, what do we have for V1? Our V1 was 33 meters per second. So 33 meters per second plus our V2, remember, was 0 meters per second. 0 meters per second, all over 2. And multiplied by time. Our variable for time, we don't know, so we're going to leave that as a t. All right, I'm going to rewrite this equation a little bit simplified. Got the meters on there, 33 meters per second divided by 2 times t. All right. Step 4, we're going to be rearranging this equation to isolate for t. So let's write that up here. Step 4, to rearrange to isolate unknown. Right. So what I'm going to do here is we need an equation where t is by itself on one side of the equation. So essentially that means this stuff here's got to go to the other side. So I'm going to do this one step at a time. The first thing I'm going to do is bring the 2 over. So since it's a division here, I'm going to bring it over and it's going to be a multiplication. So let's rewrite that here. 2 times 87.25 meters. So again, that's just bringing the 2 over. And it is equal to, the rest of the equation will stay the same, 33 meters per second times t. All right, and then the next step, we have to get rid of this 33 meters per second and bring it to the other side. So since it's a multiplication here, it's going to be a division on the other side. So let's write that out. Do this clearly so you guys can follow along. I'm showing every single step here. I'm going to be dividing by 33 meters per second, and that will be equal to time. So look at that. Now we have our time isolated. Now all we have to do is plug this into our calculator, and we will have a value for time, which is exactly what we need. So I encourage you once again, plug this into your calculator with me. Make sure you get the same answer. You get 5.2878 repeating, and that is seconds. So in our final answer, again, we want 3 significant digits to match what we're given in the question. So 3 significant digits on that is going to be time is equal to 5.29 rather. This 8 here is going to get rounded up because of the 7, so 5.29 seconds. That will be our final answer. And once again, I want to write a little statement out over here. So after the brakes are applied. So after the brakes are applied, how long will it take the car to stop? So after the brakes are applied, it's going to take the car 5.29 seconds. It takes 5.29 seconds for the car to come to a stop. All right, and just before we wrap everything up here, I just want to kind of summarize what we've learned and make sure that this is clear. So I'm going to bring this chart down. All right, so what do we know here? And I'm going to label this A1 and A2. All right, so what can we add here? We know from our answer in this question that from the time the brakes are applied until the time the car comes to a full stop, that we have a certain amount of time that passed. And that time, from when the brakes are applied until the end, when the car comes to a stop, we now know that that is 5.29 seconds. And I want to keep this here labeled. So here, this is still time is equal to 1.75 seconds. Again, this is the reaction time. When the driver initially sees the obstruction, it takes 1.75 seconds to react and apply the brakes. And once the brakes are applied, we're slowing down for 5.29 seconds. So by the time the car comes to a full stop, that means a total amount of time, 1.75 plus 5.29, that means our total time that passed was 7.07 seconds. Sorry, 7.04 seconds. And one more exercise that I just want to run through here is we know the value of the area under the curve of a velocity time graph is the distance traveled, right? So we want to double check that and know that the area of A1 and the area of A2. So we know these areas now without even having to calculate them the graphical method. We know these areas. So this area is the distance traveled before the brakes are applied. So that's actually what we found in part A over here, 57.8 meters. Rather, I'm going to use the full answer. So A1, we know, is 57.75 meters. And A2, well, what's that? That's the distance traveled from when the brakes are applied till a complete stop. And that is the distance that we used in this question. It's the 87.25 meters. So 87.25 meters. And what's interesting here is when we add these two together, the distance traveled the total distance, here, let me write that neater. The total distance traveled is equal to the area under the curve, so A1 plus A2. And when we add these two numbers together, we get an answer of 145 meters. So the area under this curve is 145 meters, and looking back at our original question, we know that the obstruction is 145 meters straight ahead. So this all makes sense. And I encourage you, with these problems, always draw these graphs and visuals to try to make sense of the question that you're given. But that's it for today. I hope you enjoyed. And if this was any help to you, please consider subscribing.